Alright everyone, so welcome back. Here is a video walkthrough of these exercises for Module 2, Linear Regression. This video is not really new lesson content, but it's also not really review, it is practice. So we get to do a couple of different things in this class. We have a little bit of the learning by reading, and the learning by writing, and the learning by watching other people do things, but if you're one of the people who thinks that you benefit from learning by doing, I highly encourage you to try these exercises yourself, spend some time with them, play with the data set if you'd like. As it says here, these exercises are for your reference. You are strongly encouraged to complete them, but do not need to submit your work and will not be graded on them. You're welcome to try these out before you watch this video, or if not, I'll go ahead. So anyway, the first one, exercise 2.1, line of best fit, or the best fit line. Draw a straight line through the graph below that you think best fits the data. Why did you draw that line? Well, I will go ahead and, not paste. I will copy that and pop over here to the whiteboard, and I will start with maybe a bad version, and then I will critique the bad version and try to do a better one. I'll go with the red pen. And how about this line here? Okay, so I've got a line that follows the data. It seems like it's reasonably close, but I do want this line to be as close as possible to the data. Obviously, it's hard to do this by eye, but one of the things I'm going to notice is there are just 3 observations above the line. There are more observations than that below the line. Also, look at the distance. This observation here is kind of close to the line, but the ones below the line are a little bit far and then a little bit far again. A little bit, wow, how about that? A little bit far, very close, very close. So I think that this line is probably not ideal. It's probably not perfectly balanced in terms of having error terms above the line about the same size as the error terms below the line, so I'll try to revise it. Maybe something like that is a little bit closer to the data on average. Either way, whatever line you come up with, I'll say is something like yi is equal to beta 0 hat, the intercept you chose, plus beta 1 hat xi, beta 1 hat being the slope that you chose, and I'll say this is yi hat. So if you give me any value of x, I plug it into the model and it gives me my predicted value for y. Then I can compare my predicted value for y, which is maybe here, with the value that actually occurs, which is maybe here, and say something about how different they were and how far off I was, which is the residual. All right, many ways of going about this, but hopefully we come up with a line that is close to the data. Obviously, in a class like this, we don't just do that by eye. We do have nice, easy formulas for where the line should be relative to the data based on things like the covariance of x and y and the variance of x, which we would use to come up with the formula for beta 1 hat. So we know that formula pretty well, and it's here on the next page here with these exercises. So we'll do that here in a second. But what it asks here is, why did you draw that line? Well, I want the line to be as close as possible to the data. There may be different ways of measuring that distance. After learning the definition of a residual, describe what you think should be true of the residuals for this line. And in fact, ordinary least squares is interesting, and perhaps this is part of why we call it ordinary least squares, in the sense that there's a reason why everybody uses OLS. Ordinary least squares can be motivated using a variety of different approaches. So, for example, I can motivate ordinary least squares by measuring the length of these residuals over here and squaring them and adding them up and making that as small as possible, which we did a little bit of calculus to do that in the other video. But I could just as easily have said, sometimes these residuals are positive, sometimes they're negative, so I see that some of my points are above the line, some of my points are below the line, and I might just say, the sum of all the residuals, which here I'll call epsilon, is equal to 0. They should add up to 0. Some are positive, some are negative. And that's equivalent to saying 1 over n times the residual. The average of the residuals is equal to 0. So that's pretty good. Now, we got that in a previous video when we tried to derive the ordinary least squares estimator. We got this notion as a freebie from one of the first order conditions that came out of that approach. There was another one, which I'm going to call, I'm going to write it like this: the sum of all the xi times epsilon I is equal to 0. And you can put a little 1 over n in front of that if you want to say it's the average of those. And it might be a little bit less obvious what this is, but that implies that the covariance of x and epsilon is 0, or the correlation between x and epsilon is 0. So I'll give you one more picture of a line over here. Here's a scatter plot, and I'll fit this line to the data. Now, I've chosen a bad line deliberately, so I can come over here and say, look, all of these error terms are positive. The data is consistently above the line, and then over here, I've got some big negative error terms. So when x is larger, further on the right, I predict these positive error terms, but when x is smaller, further on the left, I predict these negative error terms. X is actually correlated with the error terms. If you tell me what x is, I can predict whether the error term is going to be positive or negative, even if they're all 0 on average, because some of them were positive and some of them were negative. So this would be, I think we all agree, a pretty lousy line to try to fit to the data because of the correlation between the error terms and x. So maybe a line like that, which has no correlation between x and the error terms, is preferable. OLS has that property, which is here. Then there are probably a dozen other things that you could come up with as far as motivations for why you might use ordinary least squares. There's a note on my website somewhere called OLS 3 ways, which is beyond the scope of this course, but it's only 3, and it turns out there are many, many ways, many paths that lead to Rome, in this case being ordinary least squares. So different answers that you can come up with as far as what you think should be true of the residuals for your line. They should be uncorrelated with the data, x. They should be 0 on average. They should be as small as possible, making the line as close as possible to the data. All of those are good. Okay, exercise 2.2, OLS mechanics. The purpose of this practice exercise is to understand the mechanics of ordinary least squares, which is basically, here we're talking about the arithmetic that goes into it. So use the data table provided, also available as an Excel file. Use a calculator or computer program to calculate the quantities, but do not use built-in functions for linear regression and calculating residuals. So we can come up with the line on our own, okay? Instead, refer to formulas for those quantities. Textbook reference, once again, Stock and Watson, we're following here, chapter 4. So we've already calculated, I've got the average of x, the average of y, the variance of x, and the covariance of x and y. Once I get to part 2 here, I know that, yes, the slope for OLS is given by the covariance divided by the variance. Calculate this slope. And anybody who's got a pocket calculator is going to grab those two numbers right there, and very, very quickly you will have the covariance divided by the variance, which will give you the slope of the OLS regression line. And here's the picture of the line that OLS will actually fit to this data. So what I'll do is I'll pop over to Excel, and I've got those same 10 observations, and I'll start putting a couple of things together. So for instance, the mean of x. We'll say mean x. Actually, I'll do it down here, just so we can preserve a little bit of space. X bar, Y bar, covariance of x and y. And then how about the variance of x? I definitely need those. So x bar is equal to the average. Of course, Excel has a formula for the average. But if not, we all know how to do this. I would just take all of these observations, I would add them up, and I would divide by how many there were, which is just 10, and I should get 5.5. Yep, which makes sense because that would be the number that's right in the middle of this list if there were such a thing. Let's do y bar, average, of all of these observations over here. So we'll get the average of y, which should be 5.08. Okay, consistent with what the problem told us it would be. Covariance of x and y. I do believe that there's going to be a formula for that as well. So let's see, covariance. Yes, covariance comes in two flavors. There's a sample version and there's a population version. The only difference, this is going back to module 1, the only difference here is whether you want to divide by n, the number of observations, as you might in a population, or whether you want to divide by n minus 1, which is the number of observations minus 1, adjusting for degrees of freedom, which is a little bit better in a small sample to get you a number closer to the true population number. So I'll go ahead and use the sample version with the caveat, because this is an important factor, and this is a wonderful factor about the regression, which preserves the units of the data and does all of the other nice things that makes it easy to interpret and valuable to interpret in all kinds of business scenarios. The covariance.s here, which divides by n minus 1, is going to match up with variance.s, which would divide by n minus 1, when I have covariance and variance, both of them together, to make the OLS regression slope. But if I use covariance.p, which divides by n instead of n minus 1, and I use variance.p, which divides by n instead of n minus 1, I'll still get the correct OLS slope. I'll just get different covariance and variance numbers for having used the other formula there. So I'll show you that here in a second. Covariance.s. Let me grab all of these. And then I need the second set of data. Let me grab all of those. Close my parentheses, and it should spit out a value that looks like 20.2667. Let me pop it over to here. 20.2667. It's exactly as they said it would be. Good. All right. So let's do the variance of x. I'll say equals variance dot s, not x, s. So the sample variance, and it's going to be all of these, which are the x's, not the y's. Right, so there's the 9.1667, and then when I say beta 1 over here, and I'll make a box for beta 0 as well. Right here, so let's say beta 1 should be equal to regular covariance of x and y divided by the variance of x. And I'll hit the button, 2.21091. And I'll pop back to the whiteboard just to make sure that we remember. Beta 1 hat. Beta, that's a beta, I promise. Beta 1 hat is equal to the sum of all the xi minus x bar times yi minus y bar divided by the sum of all the xi minus x bar squared. Don't mind the scribble, but this is covariance of x and y divided by the variance of x. And as I was saying a moment ago, I could put a little 1 over n here, and I could put a little 1 over n there to make these formulas a bit more clear that that's what they are. And it wouldn't matter if I did 1 over n or if I put a little 1 over n minus 1. N minus 1. Ooh, didn't leave space for the little n minus 1, but I think I can. N minus 1. Perhaps that's what it says there. It wouldn't matter which of those I put, because it's going to cancel out if I put it in the denominator and in the numerator. I can clean up that sigma too. All right, a little bit more like a sigma. Okay. So that formula will work regardless of whether you divide by n or you divide by n minus 1, and it will preserve the units. So it may, in fact, be more useful than the covariance and the variance on their own. Before I make beta 0, I'm going to go over here and say data analysis, because I remember I can ask for a covariance matrix. And so I'm going to do that. I'm going to grab x and y, 2 columns of data grouped by columns, naturally, no labels in the first row, and new worksheet, sure, that's fine. Here's my new worksheet. Column 1, column 2. So the covariance of column 1 with column 1 is this number, which is the variance of x. The covariance of column 2 with column 1 is this number, which is the covariance of x and y. And then the covariance of column 2 with column 2, remember this is covariance matrix, okay? So column 2 with column 2 is the covariance of y with y, which is the regular variance of y, is this number. But if you're thinking, wait a second, 8.25 and 18.24 do not look like the 20.2667 and the 9.16667 that we had over here, you're correct. Those numbers that we just saw are covariance using the population formula where we add up all of the xi minus x bar squared, or something like xi minus x bar times yi minus y bar, and then divide by n instead of n minus 1. So it's just a little bit smaller. And I'll verify that I can get those numbers over here in sheet 1. So let me say covariance cov.p, right? So if I grab covariance p, if I grab covariance p, x with y, I should get that 18 number that we were just looking at. Sure enough, I do. And then if I say, what about variance p of x? Will I get that other number that we were just looking at, 8 something? Close those parentheses. Yep, 8.25. But if I come over here and say is equal to the covariance divided by the variance, so this is just the formula for beta 1, I should get 2.21091. Beautiful. All right, so it doesn't matter whether I've got the n or the n minus 1 in the denominator, because we're going to wash those away and map it all back to the thing that had the real units that we like to interpret. So I can look at this number and say, every time x increases by 1, the value that I predict for y is going to increase by 2.21. And this is, in fact, the line that gets me the closest to predicting y most of the time in terms of having the smallest squared error terms. All right, all of that just to talk about a slope coefficient. We calculated it. The OLS intercept is given by beta 0 is equal to y bar minus beta 1 hat x bar. Calculate the intercept. Okay, I think I can handle that. Beta 0 should be equal to y bar minus beta 1 hat times x bar, and let's see what that spits out. Negative 7.08. Okay, negative 7. Let's look at that picture again. Negative 7 down here. Yep, that checks out. That makes perfect sense that it would be down there. Okay, so negative 7 and then a slope of something like 2.21. Of course, depending on the units that you have on the vertical axis and the units that you have on the horizontal axis, that slope may look steep or it may look shallow, but if I convert these numbers, say multiply by a factor of 1,000, the slope will also increase by a factor of 1,000, and this picture actually won't move, right? It's invariant with respect to just affine transforms, changing the units of the data. The solution is a little bit more reliable than that. For each data point, calculate the predicted y. Now, I've got a formula for yi hat, which is my prediction for y every time is beta 0 hat plus beta 1 times x for that observation. So let's pop back to Excel, and I'll make a column to do this. In fact, I will even insert a column above so I can give these guys labels. X, y, and y hat. Y hat is equal to the intercept, beta 0. So I'm going to use the dollar sign here. It's equal to that value right there. And I do not want that to move. So D16, all right, that'll stay put, plus beta 1, which again, I do not want to move. If I decide to click and drag and tell this to move around, sorry, beta 1 times x right here. So just times 1 in the first case should give me negative 4.86909, which makes sense because that's minus 7.08 plus 2.21, okay? And then it should increase by 2.21, so I get minus 2.65, okay, and then it should increase by 2.21 again, so something like a minus 0.44, okay, and so on and so forth until finally at the end of the sample I've got something like 15. Does it check out with the picture? Finally, at the end of the sample, I've got something that looks very much like 15. Yes, indeed. These are the fitted values. These are the predictions for every value of x. And if you had a hypothetical value of x that wasn't one of these data sets, or data points, datums, of course, you could plug that in and say if x is equal to 1.8, right about here, I could give you a fitted value for y. X could be anything. OLS-intercept, each data point predicted y, calculate the residual. The residual is easy, right? Epsilon, this epsilon here, is just the difference between what actually happened and what you predicted. So epsilon I is quite simply yi minus yi hat. What happened minus what you predicted. Hence the sum of the squared epsilons, the sum of the squared residuals was the thing that looked like yi minus yi hat squared, right? That's just this guy. Let's make that look a little prettier. The sum of epsilon I squared, right? Sum of squared residuals, SSR, usually. Or sum of squared errors, SSE. Anyway, residuals here would be epsilon. Or you could call it y minus y hat. But that's the formula I'm going to use. So it's equal to what actually happened minus what I predicted. Now, I look at this and I say, in this case, minus 6.1 is a little bit lower than what the model predicted, so I should have a negative error term. And I'm just making sure that yep, I do. In the first case, it predicted a little bit too low. Back to the picture. The last one was a little bit too low. The second from last was spot on, and the one before that was a little bit too high. So yeah, the last one was too low, spot on, and then too high, and so on and so forth. These are the residuals. What else can I do? Calculate the sum of squared residuals, SSR. Easy. I can make a column here that's the squared residual. I'll say square resid, and that's just epsilon squared, so equal to this number, raise it to the power of 2, no sweat at all the way to the bottom, and say SSR is equal to sum of the squared residuals. Cool. Or, because I like to do things twice sometimes, there is a function here in Excel, sum, look at this, sum if, sum if s, sum product, sum squared. It will square things and add them up. One function that will square them and then add them up. So this should give me the same number if I highlight, look here, the original error terms instead of the squared error terms. And does it? Yes, it does. So that's something that happens so often. An Excel programmer somewhere decided that that needed to exist, and not bad. It'll save me the trouble of making one more column if all I want to do is calculate the sum of squared residuals or the variance of something, or you can imagine whatever else it might be. Suppose you choose a slightly different guess at an intercept and a slope. Interesting. So I could have chosen a different line. There are an infinite number of lines in the universe that I could have put on this set of axes. So I come back to my picture and I say, well, I've got the red one here, I've got the black one there, and suppose maybe I chose this line or that line, some other combination of beta 0 hat and beta 1 hat. What would you expect to be true of the SSR? Well, ordinary least squares minimizes the sum of squared residuals in order to come up with this formula. And we did that. So why? If I chose any other set of numbers, I should have a bigger SSR. Try this calculation if the formulas in your spreadsheet allow it. Well, they do. I could plug in different numbers, and you're free to do that. You know what will happen, right? I will only get larger sum of squared residuals if I plug in anything other than this beta 1 and that beta 1 and watch what happens to these guys. course, if I replace this number with something terrible, then everything is going to change. SSR will increase. Open the data set in Excel or other software to check your beta 0, beta 1 hat, and SSR. We're kind of already doing that. And then check your residuals. If you like, the last check we can do here is go ahead and grab the regression tool, input Y range, these right there, input X range, these right there. I am including labels, and I am going to ask for residuals this time. I'll go ahead and hit OK. And, oh, very nice. My intercept is negative 7.08. My slope is 2.21. I've even got an R squared and a multiple R and all of the other fun things. And down here at the bottom, I see my residuals. I recognize this negative 5.62, 0.018, 11.09. Yeah. Negative 5.62, 0.018, 11.09, 2.2109, negative 7.08. Sure enough, it's the same numbers. All right, so that's all that's happening here. And then the sum of squared residuals, you might recognize as this guy. The total sum of squares, well, total sum of squares is easy too. That would just be the sum of all the yi minus y bar. Square those and add them up, just like we squared the residuals and added them up, and you'll get this number. Then the difference between these two numbers is that, and this number divided by this number gives you r squared, and so on and so forth. The F statistic is just the ratio of these two numbers, and under the null hypothesis that nothing in this model matters, this part right here, which says how much of the original variation the model explained, should be very, very small, meaning that this thing should be very, very small, like close to 0, because the model didn't have any explanatory power. And then this p-value would be large. The f-stat works a lot like the t-statistic in the sense that you see a small p-value when you have a large statistic for the t-stat. So here, this model explained something like 2/3 of the variation in the data, which this ratio gives me a large, very large f-statistic and a statistically significant model overall. That's all that's happening there. Okay. Next, move on to NLSY.